All right, so in the last example, we were able to compute the limit of a function using the limit laws. Then we noticed at the end that we would have gotten the same thing if we just plugged our a, which was 1, into the function. And so the question is, when can you do that? And here's the answer. So this is called the direct substitution property, if you will. And so for now, we're going to apply it to polynomial, rational, or trig functions. So I'm going to pick a function that's either a polynomial, rational, or trig function, and I do want to pick an x value a that's in the domain of the function. The function needs to be defined at a. So then in that case, in this case, it turns out that the limit as x goes to a of f of x is just, you guessed it, f of a. You can just plug in for polynomial, rational, and trig functions. Now we'll talk about this more in the next section, but I do want to make it very clear to you in general, as we learned in the last section, limits do not depend on the value of the function at the point. They don't depend on f of a in general. It just turns out that for nice functions like polynomials, rational functions, or trig functions, if functions are nice enough, then this limit will always agree with the value of the function. So that's useful to know. I wanted to do an example with you right away. So let's look at this guy. So here is a nice rational function. A rational function is a ratio or a fraction of polynomials. These are both linear polynomials. And I think about this function. Its domain, you can see, is everything except x equals -3. I'm not going to write that down. I just want to be aware of that. So I know that 1 is in the domain of this function. And what that means is, when I want to compute this limit, I can just plug it in. This is just, I'm taking the limit as x goes to 1 from the left. But as we saw last time, I know that in this function, that's going to just be, plug in 1. I get 1 plus 2 over 1 plus 3. I get 3 over 4. So what about the one from the left? Well, as we saw in the last section, the limit as x goes to 1 of f of x, if that exists, then it's equal to the limit as x goes to 1 from the left of f of x, which is equal to the limit as x goes to 1 from the right of f of x. And so when I realize if I just ignored the minus sign, the left-hand directional limit, I would get 3/4. And that tells me that that has to be the same thing if I go from the left. And it's going to be the same thing if I go from the right as well. You can sort of ignore the sign, the directional limit, when you know the full limit actually exists, which we do in this case because this is a rational function. Let's do another example, which isn't maybe quite so simple. So let's look at this function. So here, I think, oh, I'll just do the same thing, right? Well, pause the video for a moment and tell me why we can't do the direct substitution property for this example. And the reason, hopefully you see, is because, let's actually write it out. We can't do direct substitution because 1 is not in the domain of my function f. I'm going to think about, let's make a better one. I'm going to think about this as my function f. So I'm looking at the limit as x goes to 1. That's not in the domain of this function, so I can't do that. But hopefully, if you haven't forgotten your algebra, then you recognize that the top is a difference of squares. So I can write this function as x minus 1 times x plus 1. I can split it. And now I can say, well, you can cancel the x minus 1s. When? Well, as long as this isn't 0, you can cancel it. You can always cancel non-zero numbers, and so the only time it's 0 is when you plug in 1. So this expression is true for all x not equal to 1. Okay, so what does that mean? So the moral of the story is that x squared minus 1 over x minus 1 looks just like x plus 1, except at x equals 1. And if you want to draw a picture, that might be a helpful thing to do. So the point is this. You can just draw x plus 1, and that is going to be what? We'll go here, And then we'll go there, and we've got the line. It looks like that. Let me let it, yeah, there we go. So there is x plus 1. And the only place there's a problem is actually right at 1. So I'm going to erase a hole there, and when you plug that in, oops, there we go. There's the hole sitting here right at 1. That's it. So now we've got the graph of this function. It looks just like this, except at 1. And at 1 there's a hole because this function simply isn't defined at 1. Well, now you can pretty easily see that the limit as x goes to 1 of x squared minus 1 over x minus 1 is just the limit as x goes to 1 of x plus 1, which is just 2. You can see it visually, right? As x goes to 1, the y value is getting closer and closer and closer to 2. And so this limit is 2. You can see it visually. You can also see it from the formula right here. When you plug in 1, you get out 2. So even though I couldn't do the direct substitution property on the entire function, I was able to reduce the function and then still at the end of the day use the direct substitution property. All right, so I want to just mention that you can do this in general. So let's write down a fact. I'm going to slide it up slightly to match our notes here. But if you have two functions and they agree everywhere except one point, so they agree for all x except a, then it turns out that the limit as x goes to a of f of x is just the limit as x goes to a of g of x. And we should say if this limit even exists. If the limit exists, then they have to be the same. And so that's really helpful in the previous example because all of a sudden it clarifies it. We realize this function is equal to this function except at the point x equals 1. And so I can just forget this guy and study this function. And I know that whatever limit this function has at 1, this one will have the same limit as well. So that's that. So let's end this video here. And in the next video, I want to look at a couple of more properties and then do some more examples with you.